this is lecture number 2 for the CIMPA course, Convex Analysis in Geodesic Spaces. First of all, there is one small incorrection in my on the board I wrote yesterday, so I have to make a correction first. So yesterday I just defined Hn to be the state of all x belongs to Rn plus 1, for which Q of x and itself equals to -1. So yesterday I wrote it this way, but actually we have to add one more condition, that x in the coordinate of n minus 1, n plus 1 has to be positive. Okay, so otherwise, if you don't have this, you will have the hyperbolic bowl here and here. So they are separated sheets, and actually we don't want these two bowls. We just need one of them. So we just want to delete the lower one, so we require the last coordinate to be positive. That's the only thing that we need to correct. Another places are good. Okay, so that's for the correction of yesterday's lecture. Now, yesterday we left off when I tried to define an Alexandra space. So I couldn't finish that yesterday, so for today I will continue on that. But actually yesterday I did not plan to talk about comparison triangle, because that is the notion to be used only in this definition, and it won't be used elsewhere. So at first I did not plan to include it in the lecture, but since we have this definition on the second day, I think I revised my lecture a little bit, and I think it's not bad to include it. So let's start from comparison triangle. Remember from yesterday we have talked about geodesic spaces. We have talked about the model space, right? That the model space will be used as a model, just like its name, for the curvature cap equals to kappa. So now we want to make comparison between our metric space, to be precise, in our geodesic space, and the model space using the triangle. So I suppose here that XD is a geodesic space okay, and we take 3 points x, y, and z belongs to x, belongs to x. The geodesic triangle with vertices x, y, and z is the union of the geodesic segments joining each pair of them. Okay, so we take x, we take y, we take z. Since it is a geodesic space, between each pair of these, we can find a geodesic segment. Let me call this CXY. We call this CYZ. And the last one, C of X, Z. Okay, but we did not assume that the geodesic between each 2 points has to be unique. So actually, CXY, for example, can be other geodesic segment if there is another one. Okay, but we just fix one geodesic between each pair, and we take the union of all the images of these geodesic segments, and we call this a geodesic triangle with vertices x, y, and z. Okay. We will write this triangle x, y, z to denote such a triangle. Now, we move to the model space. We have the triangle now. We want to construct another triangle in the model space. So, a comparison triangle in the model space MN kappa. Okay. No, M2 kappa. We will only construct a triangle in the plane. Actually, we can construct it in MN, in n-dimensional model space as well, but since it is a triangle, you can consider a submanifold of 2 dimensions. So it will reduce anyway into M2. Okay, so a comparison triangle in M2 kappa of this geodesic triangle in X is a triangle. We denote. We like to denote this with a bar, x bar, y bar, z bar, and actually this is just another geodesic triangle with vertices x bar, y bar, and z bar, where x bar, y bar, z bar belongs to the model space. I think I have to fix kappa first. Kappa can be any real. Okay. X bar, y bar, z bar. In this are points satisfying the following condition. So first, the distance between x and y, and the distance in the model space between x bar and y bar have to be the same. Similarly for y and z. These have to be the same. And finally, x and z, and x bar and z bar have to be the same. Okay, so here we construct another triangle. Let's say that we fix kappa to be 1. So now we are considering this comparison triangle on a unit sphere. So suppose this is the unit sphere. Okay, forget about the other part. This is x bar, y bar, and z bar. Okay, such that when you construct the geodesic segment joining x bar to y bar to z bar, and z bar back to x bar, you have similarity between the triangle in X, the geodesic triangle in X, and this triangle in this is M2 kappa. Let's go back to this a little bit. Okay, so X and Y here, you have to have the same length with X bar and Y bar here, and similarly for the other two. Okay, so you have kind of similar triangle, but in a different spaces. Okay, so what's next? Okay, so when we talk about comparison triangle, we have to talk about the existence of this comparison triangle. So when will this comparison triangle exist? When we were given this geodesic triangle in X. So we have a very small proposition here. Rather standard and easy to prove using like only the geodesicity of the model space and the triangle inequality. The proposition says that if let kappa be any number, so if we take 3 points that satisfies the parameter condition, that is distance between xy plus distance between y and z plus distance between z back to x is strictly less than 2 times the diameter of the model space of curvature kappa. Kappa is fixed, okay? It depends on what model space are you going to compare to. So we fixed the curvature kappa. You take 3 points such that this parameter condition is correct, holds true. Then a comparison triangle in M2 kappa exists. And by saying that it exists due to these conditions, such comparison triangle will be unique up to isometries. So that means actually it's not unique, but one comparison triangle will be isometry to another comparison triangle. So in practice, we do not care which comparison triangle we are using. Okay. So this is called a perimeter condition because this is nothing else but the perimeter of this this geodesic triangle. Okay. Now comes the definition of an Alexandra space. So we have a geodesic space XD. This geodesic space is called an Alexandra space with global curvature bounded above by some kappa in real if for any x, y, and z in x with the perimeter condition okay, so curvature bounded above by kappa for any x, y, z with this. We have this inequality, very important. Let me write it first, I will explain later. Okay, so this is the definition. Can you see it? Okay, so first we take a geodesic space, okay, XD. We want to define this, we want to verify when this geodesic space is called the Alexandra space with global curvature bounded above by kappa, quite long. There will be a shorter name later. Okay, I cannot go beyond this boundary. Okay, so okay, we will call this geodesic space, this Alexandra space, blah 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 blah, bounded above by kappa. If when we take any 3 points, okay, so we take 3 points. Let me draw it here. We take 3 points, x, y, and z. We have a geodesic triangle here. Can you see it? Okay. So this is in x. We take x, y, and z. we can construct a geodesic triangle. Okay, we need this parameter condition too. That is the condition that guarantees that we can construct this triangle and the comparison triangle. Okay, and then from this geodesic triangle, we construct in the model space of curvature equals to kappa, the comparison triangle of this triangle with vertices x, y, and z. So it may look like this. Okay, there is no need to keep the orientation or anything. It can rotate around, it can flip, as long as you have the similarity between the two triangles. Okay, and then we compare like this. We take any u, back to this definition. Okay, x is one of the vertices, and you take any u, right? What is u here? U is the point within the side y and z. So u is here. U can be any point between y and z here. Okay, so you take one point, u, and suppose this u is constructed by c of y and z at t. Okay, so c, y, z here is assumed to be the normalized geodesic connecting y to z. And we take t between 0 and 1, any one of them, and u is here. After that, we have to construct u bar which is depending on u. U bar is the point on the side y bar, z bar. Okay, and if cy bar, z bar is the normalized geodesic connecting y bar to z bar, then we can substitute t here. So, okay, y and cy bar and z bar. Okay, so u bar is somewhere here, where this this kind of construction will guarantee you that the distance between y and u in x, and y bar and u bar in the model space are equal. And similarly, the distance between z and u here in x will be the same as u bar to z bar in the model space. Okay, so u and u bar are corresponding to one another. And if you take the distance between x and u and x bar and u bar and compare them, the distance in x have to be less than or equals to the distance in the model space. So this is the kind of distance that you want to measure, this white curve, and x bar u bar is something like this. Okay, so if you compare the length of this curve with this curve, the length of the curve in x have to be less than or equals to the length in the model space, and this have to hold true for any pair of x, y, and z. Okay, so this is a way to compare the curvature, because actually the curvature plays big roles in the thinness or the fatness of a geodesic triangle. So we can define it in this way, and this kind of definition will also be in harmony with the definition for the sectional curvature of a Riemannian manifold. Okay, so this kind of comparison result was known as the Topograph comparison theorem. And due to that, we will kind of shorten the name Alexandra space with global curvature bounded above by kappa. Okay, so let me draw it here. we have a shorter name than this, Alexandrov space with global curvature bounded above by kappa. Someone might call this Alexandrov space with global CBA parenthesis kappa. That's still quite long. So I decided to follow this path. This terminology was coined by Mikhail Gromov. He was an Abel laureate, just to tell you. Okay, and he studies a lot in this area, and he coined the term CAT, kappa space. Actually, CAT stands for the three big names of geometry. C stands for Cartan, Emily Cartan. Emily Cartan is the one who studies a lot the manifold of sectional curvature less than or equals to 0. So he studies a lot of geometry of manifolds and playing with curvature bounded above but by 0. So a lot of the geometric studies in manifolds and in this kind of space nowadays thanks to him. So that is Emily Cartan. The next one is Alexandrov himself. So Alexandrov, his name. And the third one is Toponogov. Toponogov is the one who proved that the sectional curvature bounded above by kappa can be reformulated purely in metrical terms by using comparison triangles. So this notion was inspired by the Toponogov comparison theorem. So here comes the name CAT, kappa space, where we will just call it a cat kappa space. Okay. So it is the metric term of what to be understood as a metric space or a geodesic space of global sectional curvature bounded above by kappa. I don't want to say sectional curvature much because this is not the notion of sectional curvature, just an equivalent one in a manifold. Okay, so here is the definition, and here are some examples of famous cat kappa spaces. So example 1 for today. What are the nodes of a cat kappa space? So let's go back to where you don't have the curvature at all, like the linear space. So if you have a Hilbert space, a Hilbert space is always a cat 0 space. Yes, because it has no curvature. What is the next one? Any convex subset of a Hilbert space is cat 0. What else? A complete, simply connected, simply connected means it has no holes on the surface. So, complete, simply connected, Riemannian manifold. Whose sectional curvature is bounded above by kappa is cat kappa. What else do we know? A metric tree. Okay, is cat kappa for any kappa. A metric tree is a very useful one, actually, because it has greatly many applications. It can be used to explain several data types. Okay, so what are another examples? Let me see. We have another space which is very similar to a metric tree. A metric tree is a space that looks like a tree, but we also have a space of phylogenetic trees. Is also a cat-zero space. This is the space where each element inside is a tree. So it's quite different from a metric tree, for which the elements are points on the tree. But this is more like a forest because elements inside this space is a tree. Okay, so these are examples of. We have more actually. For example, if we take the tangent space, it will be cat0. If we take the space of direction, that will be cat1. What else? Products between cat kappa spaces still is a cat kappa space. If you take several cat kappa spaces and you glued them together with respect to some equivalent classes, if there are finitely many of them, then it will still be a cat kappa space. Okay, so these are examples of cat kappa space, and some of them have interesting applications as well. Okay, so looking back again to the definition, to the very definition of a cat kappa space, let's say that now we are looking at a cat-zero space. Okay, so when we're talking about the cat-zero space, that means this model space is the Euclidean plane, right? Because M2 0 is just R2. So you are just constructing the comparison triangle on the Euclidean plane. So it's the usual ordinary triangle that we all know. And when you have the right hand side, okay, so the distance on R2 will be Euclidean, okay? So then you can square both sides, right? This one is less than this one, so you can square both sides. They are non-negative, of course. When you square both sides, here is the Euclidean distance squared. So you can use the Apollonius identity, and you may obtain what is known as the CN inequality. So a geodesic space is a cat-zero space if and only if for any x, y, and z in x. Okay, so here every 3 points will satisfy the parameter condition, because the kappa, when kappa equals to 0, is plus infinity. So we have distance between x and c, y, z at t square less than or equals to 1 minus t, the distance between x and y squared, plus t times the distance between x and z squared minus t times 1 minus t times the distance between y and z squared. Okay, so this is known as the CN inequality. Okay, so this inequality is known as the CN inequality, and there is a very good point in considering this inequality. It's because we don't need to use any comparison triangle at all. This is if and only if being a cat zero. So if we are only consider a cat zero space, then this is the one inequality that you can hold on to. But what I don't like about this inequality is that it doesn't really give any perspective or understanding to the space. We understand the behavior of the space through the use of comparison triangle. That is how we come up with curvature. But actually it's fortunate to have this, because this is very intrinsic. Intrinsic means you don't have to hold on to other concepts outside the space X itself. So this is a nice inequality, and it's characterizing the space being a cat zero space. Okay, and actually here I can emphasize here that the cat zero space, any cat zero space, is uniquely geodesic. Okay, actually we can prove using this CN inequality that there cannot be two geodesics between two different points. Okay, so CN inequality is the useful inequality. Actually, it's kind of a Apollonius identity, but you replace the equal sign in Hilbert space with less than or equals. And when you are in a cat kappa space, it's very lucky that we have very similar inequality like the CN, but it's not called CN, of course, because CN is the French word standing for negative curvature. So when we are talking about kappa being positive, it's not relevant to say that it has negative curvature. Oh, by the way, this theorem was proved by Bruhat and Tits, I think from 78. Did I have some note? No, from 72. So this is Bruhat and Tits from 72. And another one, so XD is a cat kappa space whose diameter is less than d kappa over 2. Then you can find C kappa positive, such that the distance between x, cyz at t squared less than or equals to 1 minus t, distance between x and y squared plus t times distance between x and z squared minus. So here ck comes into play. C kappa comes into play. And then times t times 1 minus t times distance between y and z squared for any x, y, z in x and t in 0 to 1. Okay? So this is the same as, it looks similar to CN inequalities, except that we have C kappa here. Okay? So we can roughly say that, okay, when kappa equals to less than or equals to 0, then C kappa is 1. We can somehow say it like that. Okay, but here, when kappa is positive and diameter is less than d kappa over 2, then we have C kappa here, which is not 1. Actually, we have a very specific form of C kappa. It is diameter of x itself times the tangent of d kappa over 2 minus diameter of x. Yeah. Too bad I did not take a note what C kappa is, but I'm pretty sure it's this value. And this value, if you plot this curve with diameter x as the variable, you will see that as diameter x approaches d kappa over 2, then this C kappa tends to 0, and when the diameter here reduces to 0, then this C kappa here will go to 1. Yes. Okay. So you can try to plot the graph and see the behavior, and that means if you are familiar with geometry of Banach space, this roughly means that the distance squared is strongly convex, okay? And the strong convexity modulus is given by this. It reduces as the diameter touches d kappa over 2, and it increases as the diameter grows very, very small. Okay, so this is all you want to know about the space. Took lots more time than I thought. Now we can go to the second topic, which is the convexity. So I will adjust the talk to cover all of them, but the detail or the arrangement or the order might be a little bit different from what I said yesterday. I try to cover all of them. Okay, so the next topic is about convexity. If you remember at my very beginning of the first talk, I list the topics. There are 5 of them. This is the second one. Okay, so we talk about convexity, or to be precise, geodesic convexity. Okay, so suppose let me recall you first. So when you have a cat-kappa space XD with diameter of X let me write it like this, with du and v less than d kappa over 2 for any uv belongs to X. Is uniquely geodesic. Okay, so this can be a little bit different. This can be a little bit different than saying that the diameter is strictly less than the kappa over 2, because when you have two elements inside the space, the distance between two elements inside the space being strictly less than this, it means when you take the supremum over u and v in X, you can have the diameter equals to d kappa over 2. Okay, so that can be a little different. So if X is a cat-kappa space and has this property, then X is uniquely geodesic. That means between 2 points, you have only one geodesic connecting them. So we will use the following notation. One minus tx. I will call this a plus, even though it's not really a plus. I will say it is a plus. Okay, it's just my pronunciation of this symbol. So what is it? What is this actually? It is cxy at t, and this is defined for every x and y in X, and I will define this for every t in the interval 0 to 1, where, of course, cxy is the normalized geodesic. Joining X to Y. Okay, so we will develop this notation. We will use this notation from this point on. Now the definition of a convexity, of geodesic convexity, very simple and very natural. So a subset C of X. This is any subset. C can be X. There is no restriction. If I want to stress that C is a strict subset of X, I will write it like this. Okay. So as a convention, this is any subset. A subset C of X. X is this cat-kappa space with this condition. So subset C is said to be convex. And since this is the first definition, I will emphasize when I put something in a bracket, that means later on I will drop this. I will tacit this term. Said to be geodesic convex. if okay, I will come back to this notion. Okay. Okay, so we will denote the geodesic segment joining x to y by this interval notion. So this is the segment joining x to y, including x, including y. Okay, this is just the image, right? The whole image of this geodesic function. Okay, so a geodesic convex subset, geodesically, I think grammatically, it has to be geodesically. Okay. So this subset C is said to be geodesically convex if taking any 2 points within the set, you have the geodesic segment joining them lying also inside the set. So you have the set C being something like this. Okay, we are staying on a surface. Okay, x may be like this, and if you take 2 points, x and y, okay, then the geodesic segments joining x and y is lying wholly inside the set C. When I say inside, it means they are elements of C. I did not mean it's the interior of C. Okay. And okay, so C here is convex. Okay, so suppose we have another set here. Let me call these S. Okay, if we take 2 points, x, y here, then the geodesic segments joining them may be something like this, but there are parts of this geodesic segment that is outside of S. So S here is non-convex. Okay, and for the convexity, you need to check this condition for every pair of x and y, every possible pair of x and y inside the set C. Okay, well, okay, the negation of convexity, if you can find one x and y for which the segment lies partially outside or wholly outside of this set S itself, then it's non-convex. Okay, so this is the definition of a convex set, and for this afternoon I think I will, okay, we are not finished, we are just having a pause, so we will pause here for about 5 minutes, and then after that we will see some examples of convex subsets. Okay, so see you in 5 minutes, guys. Okay, so let's continue with some examples of convex set. Let me see, what do we have here? Okay, so let me call this example 2 of today. So what are the examples? Okay, so the first one is the space X itself is convex. Okay, and more extremely, the empty set is convex. It's convex, but it's not useful. Okay, the other one is the segment. So this is convex. Okay. Okay, so when we say any segments, that means x and y are coming from x, of course. Next, any balls, open or closed, okay, b of x are any balls is convex. But we have to note, okay, so for this example, we have to note that when kappa is positive, we have to make this assumption, okay, otherwise we will not have that convexity. I will come back to this again, okay, so I will mark a star here. Okay, so a Cartesian product of convex sets is again convex. Okay, of course in the product space. Any intersection arbitrary I can drop this, an arbitrary intersection of convex sets is again convex. And by arbitrary, I mean finite intersection, infinite intersection, just any intersection of convex sets is convex. Okay, you can see this not so difficult. And you may be able to guess that to show the convexity of this ball, actually we have to use the inequality that I showed you. So if kappa is less than or equals to 0, then there is no additional condition. But if kappa is positive, then we have to take care of this example because the inequality that I showed you around here, I just erased it. Okay, that inequality holds true only when the diameter of the space is strictly less than d kappa over 2. Okay, and that inequality plays a great part in showing that this ball is convex. Okay, so in general, we can say that if R is strictly less than d kappa over 2, then the ball is convex. We can say that in general cat kappa space because that ball will again be embedded in a smaller cat kappa space satisfying that diameter condition. Okay, so we can show somehow like that. But if the radius is too large, then the ball will no longer be convex. Let's see with this illustration. Okay, so we can take for instance S2, the unit sphere of R3. We can draw it like this. Okay, we fix any point x. Let me fix it here. And then we take a ball with radius r larger than pi over 2. Okay, larger than or equals to pi over 2. Actually, we can take pi over 2, and you can still see that it's not convex. Let me take it pi over 2. Okay, so the upper half, upper hemisphere, this is ball of x with radius pi over 2, right? Because when you measure the distance from x to any point on this line, the distance, the length here will be pi over 2. And what's wrong? What goes wrong here? Okay, so what goes wrong here? If you take a point x, no, not x, we have x already. Let's take y here, and you take z to be the antipodal point of y. Okay, y and z. Okay, and actually you can notice that if you go down, this is like a half circle that connects y to z, down to passing the antipodal point of x. Okay, if you go past through like this, then this red curve is also a geodesic, and it violates the definition of convexity because we need the geodesic segment connecting 2 points in the set to be lying on the set itself. But here we can have a geodesic segment connecting 2 points in the set, but it lies completely outside the set. Okay, so when the radius is larger than or equals to pi over 2, then this ball is no longer be convex. You can increase the radius of this ball as well. That will be more obvious. Okay, so if you take x here, and if the radius is very large, then it will cover this upper part of the circle. And if you take x and y, something like this, not x, you take y and z, and you can construct similarly the geodesic segment connecting them is forced to be outside. We cannot choose because here y and z are less than pi over 2 apart. So the geodesic segment that joins y and z is forced to be outside the set, the ball. Okay, here actually you can use this as the geodesic segment, but you can choose some of them to be outside. But in this case, it is forced to be outside. You cannot construct a geodesic segment inside the ball. Okay, so this is what can go wrong in kappa space with kappa positive without the diameter condition. Okay. It's quite annoying to tell you the truth, the fact that we need to keep in mind this diameter condition always when kappa is positive, but that's the restriction, that's the price to pay. Okay, so for a non-convex set, we can convexify it using a convex hull, and it's defined like this. So if S is not convex, we can best approximate it. It means S with a larger convex set, minimally, by taking the convex hull, which is defined as follow. The convex hull of the set S is defined to be the smallest convex set containing S. I use the because this convex hull is uniquely defined, and actually it is the intersection of any set C, subset of X, such that C is convex and S is a subset of C. Okay, we take this intersection. Of course, you take C, which is convex, then the resulting set, which is an arbitrary intersection of convex sets, is again, it is convex. And since S is a subset of C, this intersection is a superset of S. And sorry, S is a, okay, that's correct. S is a subset of C. That means this intersection is a superset of S. And this is, by the way, the smallest convex set that contains S as a subset, because if you have another convex set that contains S, then that set has to go inside here and will be intersected away. So it cannot be any, there cannot be a second smallest convex set containing S other than this. Okay. Another property which is crucially important when we talk about a convex set in this setting is the following theorem. Before that, this is an invitation for you to solve difficult problems. This is an open problem. It's very surprising because the problem is very simple, but up to now it remains open. So, is the closure of the convex hull of finite set compact? It's very simple. If you don't like CL here, you can just take closure like this, okay? So of course, when you are in linear space, this is compact because this is just a polytope and it lies in, it is closed, it is a polytope and it lies in a finite dimensional space. But when we are in the Kappa space, the questions of whether or not this set is compact is unknown. Even for the 3 points, x1, x2, x3, even for that, we still don't know. Okay, it's a very interesting open problem, and actually, when you try to prove something in this setting, a lot of time you will go back to this open problem and you cannot solve that. I encountered this problem like many times, and of course it remains open. Okay, so next one is a theorem which is very useful and very essential for convex analysis. So if all of the results here, we assume that X is a Kappa space satisfying the diameter condition. Okay, so if X is complete, and Of course, I will write it again to emphasize. Because X is, of course, a Kappa space. Before, we did not assume completeness on the space, but here we have to assume completeness on the space. Okay, the diameter condition. Okay, so we take a sequence Cn, okay, which is a decreasing sequence of non-empty closed and convex sets. That means when you take C1, C2 have to be a subset of C1, and C3 have to be a subset of C2, and so on. Okay, so decreasing in the sense of subsets. Then what do we gain out of this? We get the intersection of all the sets. Cn is non-empty. Okay. This is the result by so this is a result by Espinola and Fernandez-Leon. I did not make a note, but I think so. Um, 2009. Okay, so if you are again familiar with geometry of Banach space, this kind of decreasing sequence of non-empty closed and convex set having non-empty intersection is equivalent to the fact that that normed space is reflexive. And here you can see that, so we roughly say that a complete Kappa space with this diameter condition is kind of reflexive. Okay, we don't have the word reflexive here because we don't know what a dual space is, right? Reflexivity means the second dual is, reflexivity, yes, the second dual is isometry to X, right? Normally you only have X being embedded isometrically in the bidual, but if the bidual is also isometry to X, then it's reflexive. And here we don't have even the first dual space, so we cannot speak of reflexivity in terms of duality. Actually, there are some attempts to define what is known as the dual space, but I will talk about this on the last lecture, and I will tell you why this kind of ideas is not so relevant in the setting of Kappa space. Okay, so this is all about convex sets. Now we want to use the convexity here to define a convex function. Okay. So we consider a function f, okay, defined on X into this. Okay, I tried since the first lecture to avoid using this kind of bracket. Okay. So here we include plus infinity, but we somehow exclude minus infinity because that's not so interesting. Actually, if we impose full condition, convexity, properness, and lower semi-continuity, then if we include minus infinity and f takes the value of minus infinity at a point, then the function is minus infinity everywhere due to the lower semi-continuity, and there is no use dealing with that kind of functions. So we can safely exclude minus infinity here. And we say that f is convex. Okay? If for any xy in x and for any t belongs to the open interval 0 to 1, we get f at 1 minus t x plus ty less than or equals to 1 minus t of f x plus t fy. I don't like using we get when we define things, so it holds. Okay, so one may ask, why do we need to exclude 0 and 1 here? Actually, you can include what happened when t is 0. When t is 0, then this, let's call this convex combination, okay, even though it is not so much the combination as in linear algebra, because it's not really a plus. It's not an algebraic operation. Okay, so this convex combination reduces to x. Okay, and what about this side? This side, t is 0, right? For okay, t is 0, so we may delete this term, and this is 1. So fx is less than or equals to fx. Not so interesting. How about when t equals to 1? When t equals to 1, this reduces to fy. This disappears, and this is fy. So fy is less than or equals to fy. Not so interesting. But there is one more reason that I exclude. It's because I don't like to make convention like 0 times plus infinity is 0 and so on. I don't like making this kind of convention, because notice that we include plus infinity in the value of f, right? So let's say that at the point x, the value of f is plus infinity. So when t equals to 0, okay, this is f of x. What is the right hand side? Okay, oh, sorry. Let's say that the value at y is 0. So, no, sorry, it's plus infinity. Fy is plus infinity. And take t equals to 0. This reduces to fx. This reduces to fx. How about this term? This term is 0 times plus infinity. So what is 0 times plus infinity? We don't know. Even in the limit, that is still indeterminate form. So if we want this inequality to make sense, we have to make a convention. Okay, if we include t equals to 0 and equals to 1. So excluding 0 and 1 does not hurt, because that's the obvious case. So I prefer to leave it this way. And if you include them, 0 and 1, you have to make sure that you make a convention that 0 times plus infinity is whatever you like. 0 or plus infinity, verify. Okay. When t equals to 1, it also happens here, because this can be 0 and this can be plus infinity. So we exclude them. Okay, so one more theorem. Not really a theorem, more of a proposition. F is convex if and only if you have the epigraph of F. So what is an epigraph? It is the set, some set is convex. Of course, in x times r. Okay, and what is an epigraph? Epigraph is the set, the pair of point x and a value lambda. Okay, this is in x times r, such that fx is less than or equals to lambda. Okay, so it's just the area above the graph. That's why we call it epigraph. So above the graph. And if we want the area below the graph, then this inequality will be reversed, and that is called the hypergraph, the area below the graph. This is not new. So if this is the graph of F, epigraph is just the area above the graph. So this is epigraph. Okay. If here, from this point on, f takes the value of plus infinity, then the epigraph is just ends here. There's nothing here that is considered as an epigraph. Okay, so this epigraph has to be a convex set in this product space. X is a cat-kappa space. R is real line, cat 0. So the product is cat-kappa space. Okay. I think I may include lower semi-continuity here in the same proposition. So F is lower semi-continuous. I write it as LSC. Okay, that's a well-known abbreviation. F is lower semi-continuous if and only if the epigraph of F is closed. Of course, closed in x times r. Okay, so we have like 2 items. Another proposition. The previous proposition deals with epigraph, but this proposition will deal with sublevel sets. Convex. Here we have only one side implication. Okay, it's not if and only if. Okay, if X is convex, then the sublevel set of lambda. Okay, so what is this? This is a convex set. Okay, so what is this sublevel set? It is the set of all x, in capital X, such that f of x is less than or equals to lambda. Okay, there are some similarities between epigraph and the sublevel set. So the sublevel set actually is just that inverse image of minus infinity to lambda. Okay, nothing new. And for this, it is only one-sided implication. There are functions for which every is convex for all lambda, sorry. There are functions for which all the sublevel sets are convex, but the function is not convex. Okay? You have plenty of them. For example, the Heaviside function, Heaviside step function. Where do I draw? Here. The Heaviside is defined like this. So I will use the lower semi-continuous version. So the value of 0 is 0. The value at 0 is 0. And if x is negative, then the value is 1. Okay, and here is 0. You can see that every sublevel sets are convex sets, but this function is not a convex function, because when you take the epigraph, okay, so this is the epigraph. It's not a convex set because you can take, for example, points here and here. It's outside of this epigraph, so epigraph is not a convex set. Okay, and this is a function for which all of the sublevel sets are convex, but the function itself is not. Okay, so beware here. The function for which all the sublevel sets are convex is called a quasi-convex function. Okay, it's not a convex function, but a relaxed version of convex function called the quasi-convex function. The other item is when f is lower semi-continuous. Here you still have if and only if all the sublevel sets is closed. Okay, these are results that resembles what happens in linear spaces, in Hilbert spaces, in any spaces with curvature 0. Let's see some examples. I will not say much, but just enough for you to continue. So this is example 3 for today. Okay. So if we fixed a point x in the space, the function that maps y, okay, y coming from x to the value distance of y and x. So this is a convex function. Under the same assumption that the diameter of capital X is strictly less than pi over 2, okay? What else? So if C is a closed convex set, then the function y, okay, y again coming from x, maps to inf. Actually, we have the symbol, the notation, like this. dc of y, which is nothing but the infimum of x from the set C of the distance from y to x. So it's the distance between y to the closest point of C. Okay, so this is a convex function. Next is the indicator functions. So if C is again, here we have to assume non-emptiness. Okay. Actually, if C is non-empty, then this infimum onto empty set is just plus infinity and it's convex anyway, but that's not so interesting. Next, if C is non-empty, closed, convex, and IC defined on x into minus infinity with plus infinity included. So if this function is given by IC at x is defined to be 0 if x belongs to C and to be plus infinity with x not in C is convex, lower semi-continuous, and proper. If you do not know about properness, properness means there is a point where the function takes finite value. Okay, it's not everywhere plus infinity. It has to take finite value somewhere, and that is what we call proper function. Okay, so these are some examples of convex function. We also have if f and g convex, then so is their summation f plus g. Okay. If we change plus to minus, then it's not true. Okay, that's very obvious because, for example, you can take like one of these to be a parabola and another one a convex parabola, another one to be 0 everywhere. Then 0 minus that convex parabola is not convex. It's like this. It's not convex. So these are standard examples of convex functions that we might encounter in the future. But somehow the convexity is not sufficient to study several things, especially when we talk about the existence of a minimizer. When you have a convexity, it's nowhere close to having a minimizer. You can have a convex function which is also continuous and don't have any minimizer, for example, the exponential function. So we have to develop another version of convex functions which is stronger in a sense. And this strong version of convex function plays a very, very important role in the subsequence. F is said to be strongly convex. So we want to define a strongly convex function, and strongly convex function will comes with a modulus k. Okay, so we say that this is a strongly convex function with modulus k if we have this stronger inequality. So the value of f at 1 minus tx plus ty is less than or equals to 1 minus t of fx plus t of fy. So this is the convex part. Now comes the strongly convex part, minus with some k. Some k here is actually the modulus times t times 1 minus t, and then the distance between x and y squared. And this have to hold true for any x and y in the space, and any t from the open interval 0 to 1. You might think this looks a little familiar. It's because if you replace this f with distance squared with one of the input fixed, then this is just if kappa is less than or equals to 0, this is Cn inequality. If kappa is positive, then you have the strong convexity of the distance squared function with k here equals to c kappa. Okay, that was the result of Shinichi-Ota in, I don't remember correctly, I think it's 2007. Let me check. I think I have the reference. Yeah, Shinichi-Ota 2007. Okay, so this is the definition of strongly convex function. What makes the convexity stronger? It's this term. Okay, so this is a negative value because all of these are positive, and you have negative value, a negative sign here. That means not only this one is larger than f on the left hand side, but we subtract something from here, from this, we subtract something from this, we still have a larger one compared to the left hand side of the inequality. Okay, and what I imagine of a strongly convex function. a strongly convex function, we have a good convex function that we have in mind is the quadratic function, which looks like a parabola. Okay, and a strongly convex function means the function which is more convex than some parabola. More convex than some parabola. It can be something like this because you can support this function with you can support, okay, again. Okay, so suppose this is f. You can support this function f with this parabola. Something like that, okay? So this, if you can do something like this, then this f is strongly convex function. You can judge by the strong convexity by just looking at it. And if f is just an affine function, so f here is just an affine function, then it's not strongly convex because whichever parabola you draw, it will the parabola will go above f. Okay, you cannot find a parabola which supports f. Okay, no matter how flat is that parabola. Okay, the camera is moving with me. Okay, no matter how flat is the parabola, it will still go above this affine function somewhere. Okay, so this affine function cannot be strongly convex. Another good example is x to the power of 4. This is just plainly function from R to R, okay, just to give you some idea. Okay, so this is x to the power of 4, which looks like a parabola, but it's not. This cannot be, excuse me, this cannot be a strongly convex function because of the exponent. Okay, so x to the power of 4 is very, very flat in this region -1 to 1. Okay, any parabola will go something like this, will get above this, because in this region x to the power of 4 is very, very flat. It's more flat than any choice of parabola you choose. Okay, so that's about strongly convex function. So what are the examples of strongly convex function? Example 4. Of course, the distance squared when one of the input is fixed is strongly convex. Okay, and once again you have to keep in mind that the diameter of x needs to be strictly less than d kappa over 2. We have another 2 examples which are very, very important. So if you have a family f lambda, where lambda belongs to any index set I, if this is a family of strongly convex function having a common modulus k. Then we take the supremum over all the functions. Okay, the function f defined by the supremum. This is strongly convex. With the same modulus k. Another important example is a sequence, and instead of taking the soup, you take a limb soup. Again, you have to have a common modulus k. Then you define another function f by taking the limb soup. By taking the limb soup over n goes to infinity of fn. This is again strongly convex with modulus k. Okay. The important part is that you have to make sure that all the modulus is working for all the functions in the sequence. And the proof is not difficult at all if you go back to see the very definition of strongly convex function with modulus k. So for example, if you take a soup here, you just replace this f with f alpha. Okay, so this inequality holds for every f alpha, right? And k here is common. And then you take the soup. On the right hand side, you push the soup into each one. Okay, you don't have alpha here, right? So the soup only goes here and here. In the inequality, of course, you cannot split the soup with equality. Okay, so you split the soup with inequality on the right hand side, and then you take another soup on the left hand side. You get the result. Okay. Now, if you have a sequence here, so f is replaced with fn, f here and here replaced with fn, and then you take limb soup both sides. Okay, so you split limb soup using the inequality here and here, you get the result. Okay. Now I think we can talk a little bit about the minimizer of convex functions. Why do we need strong convexity? Because we need some effects, some special effects on the minimizers of the function. So the theorem goes like this: if f is convex and lower semi-continuous, then we have the following. Okay, we can just write it here. If f is convex and lower semi-continuous, then f is bounded on bounded sets. Okay, so if you restrict yourself to a bounded subset, and you take the supreme, and then you take the infimum of f over that bounded set, then that infimum have to be finite. It will not go to minus infinity. And the proof of this is not so difficult. Oh, I just realized the statement for decreasing sequence of sets, of closed convex sets. Those sets have to be bounded. Okay, it's not any. So Cn here have to be non-empty, bounded. So I forgot to add the condition of boundedness. Okay, convex and closed. Sorry. And if you have all these, then the intersection of Cn is non-empty. Okay, boundedness is important. I think the reason that I forgot is because I emphasized the fact that the diameter of x have to be less than the kappa over 2, which is a kind of bound in my head. Okay, so in the case kappa less than or equals to 0, we need boundedness. But for kappa positive, every set is bounded because we require the diameter condition to be less than or equals to like pi over 2 root kappa. Okay, so we need the boundedness here because we want to apply that reflexivity result. Okay, so we take, the idea is very simple. You take S lambda, SF lambda, and you take lambda goes down to minus infinity, right? If you can do this, then using the nested non-emptiness of the nested intersection, then you have function being the value of the function being minus infinity somewhere. And next, this is the last sentence for today. So if f is strongly convex, okay, and lower semi-continuous, of course, then f is bounded, bounded below okay, f is bounded below and the infimum is attained. Uniquely attained. So this is why we need the strong convexity, because we want to improve the lower bound. So first, F, if it is convex and lower semi-continuous, only then it is bounded below on bounded sets. But if we expand the set to be the whole space, which is not necessarily bounded, then we cannot say anything about the lower bound of F. But if F is strongly convex, then F is bounded below. Okay? And when F is bounded below on the whole space, we can somehow show, using the same technique here, that the infimum has to be uniquely attained. This means if F is strongly convex and lower semi-continuous and proper, of course, properness is always hold for this. If we have that, then F has a unique minimizer. This is another way to put this sentence to work. Okay? And that's for today. We have seen some convex sets. We have seen the convex functions. We have seen a stronger version of convex function, which helps us to obtain a minimizer. Okay, that's for today, and let's see you tomorrow. And tomorrow we will talk about how we will use this kind of strong convexity and apply it to another kind of theory. Okay. Okay, see you tomorrow.